Hello, everyone. My name's Corey Smith, and today I'm going to be talking to you a little bit about tempering materials. Just a quick overview before we do get started. I'm going to have an introduction section, just kind of give you some preliminary knowledge on some of the things that we will be talking about. We'll talk about mechanical characteristics, materials and methods, findings and results, and then a relation to how this goes along with the 3400 course that we have been in. So to start off with our introduction, as you may assume, manufacturing or producing any product within pretty much any field is going to require well more than just a small amount of consideration or knowledge of the materials that you are working with. Definitely want to have a good knowledge of these materials and how you can alter them, just in-depth know-how into the certain traits that they do have and what methods we can use to change those to achieve successful results. Every material or alloy will have its own unique and identifiable characteristics, and some of those may be desired, some may not. So we want to know what we can do or how we can go about diluting some of the less desirable traits and magnifying some of the ones that we actually do want. Some of the mechanical characteristics that we may, there are many, but some of the ones that we're going to talk about today are strength, toughness, ductility, and stiffness. And then, although there are quite a few, heat treatments as far as annealing, hardening, normalizing, the one that we're going to be, as mentioned before, discussing today is tempering. So before I go into this, also a little background on tempering. It's, like I said, a heat treatment technique, and it's been around for quite some time. The oldest actual known heat-treated material that was tempered was a pickaxe, and it was found dated to somewhere around the 1200 to 1100 BC era. So it's definitely been around for a while and stood the test of time. So a couple of mechanical characteristics, we'll keep going. Toughness, some of these get a little confusing because in normal everyday life we do use toughness and strength as kind of a interchangeable phrase. So for toughness, this is actually going to be something that's going to withstand shock. It's the ability to. It's actually the opposite of brittleness. So not necessarily ductile, but glass would be brittle. It's not able to withstand the shock. Once it reaches a certain point, it's going to shatter. So a tougher object will not be doing that. Strength is just the ability to resist deformation under a loading. Hardness is one that we are familiar with. Diamonds, per se, they're scratch resistant, resistant to bending, penetration. Ductility, for example, copper, gold, very easily drawn out into thin specimens. Stiffness is going to be the resistance of elastic deformation under a loading. It's very modulus E dependent. So with tempering, it's going to be used to improve the characteristics of many metals, particularly steel. For example, some are bolts, nuts, knives, knife blades, drill bits. Those all undergo tempering process. It's typically done after a quenching of a metal, because that will cause a metal to become very brittle. We can see in the picture to the left, the tempering process definitely didn't go as planned, and therefore it was a bit brittle knife blade. On the right, you can see a graph that kind of correlates hardness and toughness into one, so you can kind of see that relation, especially with a heat treating process. Like I said before, it is typically done after quenching. So the hardening process actually takes a material nearly to the melting point, and then we quickly cool that material off, usually in a water or an oil. The tempering's then done afterwards, and we bring that material back up to a certain heat after it has been converted to a martensite. And we hold that material at a certain heat below the that lower critical temperature for a given amount of time. And on the right, you're able to see kind of the process. The quench is that vertical line down, and then we reheat it back up in some type of a furnace or a kiln. And depending on what properties you want, you may keep it in a little bit longer or use a higher heat. And then we want to just slow cool that material down afterwards to retain those qualities that we obtained from the tempering. The temperature, like I said before, is definitely going to determine how much hardness you remove from that metal. The higher the temperature, the more hardness is going to be removed. So definitely want to keep that in mind whenever we do this. And there are a lot of graphs and properties out there that we can look into depending on which metals we are working with. So here we've got just a good visual. The tempered steel, this one was actually normalized prior to tempering. And you can see as the temperatures go up, we actually do get a little bit of a change in color. So in some ways you're able to kind of see just by coloration how much heat has been applied to it in that tempering process. The color itself is actually formed by an oxide layer. It just forms on that surface. Higher temperatures create thicker layers of iron oxide, and so do longer time frames spent in that temperature zone. The layer actually does help to prevent the steel from corrosion. For our findings and results, we previously mentioned that tempering is mostly focused on metals or materials that have iron in them, or ferrous ones. And it usually does come after a hardening process, whatever that may be. They're expected to go under a heavy stress, or they're going to be required to in some kind of an application, and we want to do this tempering to avoid fracture because it will add ductility as well. The metal, after being heated for that long amount of time and then quenched, it's going to be very brittle. So we want to do this to kind of counteract some of those without totally getting rid of that strength that we put into the metal in that quenching period. And just quick kind of overview of how this does pertain to the 3400 course. In chapters 9 and 10, we talked about phase diagrams. This in turn allowed us to be able to look at a graph or a diagram and see which phase a product would be at a given time and temperature, and also with temperature and a composition of an alloy. So if we've got one, a little bit more of one over the other, how that will affect things. And it definitely, along with temperature, is going to greatly affect where we lie on that phase diagram and which percentage of phases are going to be at certain points. And then in chapter 10, we went a little farther into it and actually saw once again that time and temperature are both it's going to be big dependent on time and temperature. And after that initial heat treatment, the high temperature, we're going to drop it back down to the really quick cooling martensite, and then strong and brittle. And then we will bring it back up to that eutectoid line right below it, and hold there for a certain amount of time and be able to get some of that brittleness out, add a little ductility back, and retain some of that strength. And then right here we have just cool diagram that I've found online, source to the left, just shows how much tensile strength was added to fasteners. These are bolts, just because of that tempering process. So that's pretty cool. And then here are my sources, and I appreciate you all for listening in.